In 6141, we investigated algorithms for designing a robot which, given a map of the environment it is in, autonomously travels to some destination point while navigating around potential obstacles in the space. Designing autonomous vehicles that can navigate complex environments has many practical applications. For example, Google Car was built to autonomously navigate amid traffic. One major challenge for autonomous cars includes reliably detecting bicycles on the road. To design safe, autonomous robots, it is important to investigate algorithms for planning, control, and perception. We use these principles to design a robot that navigates around the STATA basement loop, while steering right around green cones and left around red cones.
We first specify a path around the loop for the robot to follow. The path is represented by a list of coordinates on our map. Points are deleted as the robot passes them. Cones in the way of the robot also cause the path to update. When a robot encounters a cone, we update the path by computing the coordinates of the desired point and adding this point to the path. The desired point is set to be a safe distance, delta D, away from the cone, so that the robot navigates around the cone before continuing on the original path.
To localize, our robot approximates the distance it has traveled using odometry data. It then checks this estimated precision against measurements from its laser scanner and compares them against the map to localize more precisely. To detect cones, the robot continuously checks its camera image stream for sufficiently large orange and green blobs. This generally works when the robot's environment does not have any other orange or green artifacts. We determined the orange and green color ranges by collecting data about the pixels in the cone image. To encode the colors, we choose HSV, hue, saturation, and value, instead of RGB values, because HSV is less sensitive to lighting conditions. We then draw a bounding box around the cone to ensure we capture it entirely. After detecting the cone, we determined the cone's relative distance and angle. We used the area of the bounding box to estimate the cone's distance from the robot. In particular, we fit a polynomial equation relating the area of the bounding box to the cone's distance from the robot. We then compute the angle in a similar way using its position in the image.
The robot follows the path using a pure pursuit trajectory controller. The pure pursuit controller computes the angle the robot needs to steer at in order for it to go from its current position to the next point on the path. We send a command to the robot telling it to steer at this angle and drive at a constant speed. After integrating the planning, perception, and control algorithms, we discovered some issues with the approach.
One significant issue with the cone blob detection algorithm is that the robot would still sometimes classify other objects, such as the exit sign and fire extinguisher, as cones. To prevent misclassification, we blacked out the top half of the image so that the robot would ignore anything near the ceiling. Other red objects, such as the red curtain and red locker, appeared in the bottom part of the image and hence were still misclassified as cones. To resolve this, we compute the map coordinates of the detected cone-like object and check whether the object is near a wall. If it isn't, we classify the detection as a cone. While our robot is generally able to navigate around cones, it has issues planning a proper path if a cone is located at a corner. When it passes a cone at a corner, the robot adjusts its path, but the path cuts across the wall and is infeasible. This may be resolved if we add more points to the path along the corners and requires further testing.
Planning, perception, and control algorithms all need to be integrated to enable the robot to successfully navigate the space. The results show that a robot can use its sensors to localize and avoid known obstacles and walls based on the map, while also sensing new obstacles not present on the map. It can estimate the location of these new obstacles on the map and respond appropriately. This capability is important because in order to integrate autonomous robots into human life, they must be able to complete their tasks while responding to static and dynamic obstacles.